Hey there, this is Organic Chemistry Simplified, and our goal here is to make organic chemistry simpler. Today we're going to learn how to tackle a synthesis problem with confidence by developing a framework for dealing with these types of problems. And we're going to learn a little bit about carbonyls in the process. So what better way to develop a framework for attacking carbonyl synthesis problems than with an actual problem? Okay, so let's get to it. The first step in the framework is what is the same in your starting material and your product, and what's different. So right away we can see that here it's pretty much the same, except now as we can see, these two entire parts are the same. So now what's different? It's this hydrogen, and it's replaced by these two alkyl carbons. Okay, so the second step in the framework is, what are the specific changes that are made? Well, we just went over it, right? It's what's different. It's that we replace this hydrogen with these two carbons, right? So the next step is, how do I make each specific change? Keeping in mind that it may take multiple steps. So the change that we need to make is to go from this hydrogen and replace it with two additional carbons. So how can we actually carry out that change, right? Well, there's probably nothing we know that can go straight from a hydrogen to two carbons. No mechanism we know is going to deprotonate that hydrogen. First of all, it's not the most acidic hydrogen, and it's going to allow us to attack a two-carbon chain. So what we probably want to do is to turn that hydrogen into a leaving group and then attack with an alkyl chain so we can tack on these two carbons, right? So the first thing we need to do is make that hydrogen into a leaving group. Well, again, we can't do that in one step. We don't know any reaction that allows us to go straight from a hydrogen to a leaving group. But we do know is a reaction that allows us to go from a carboxylic acid to a leaving group. So we're going to go straight to a carboxylic acid from this aldehyde we have here. So how do I make a carboxylic acid? Well, we're going to oxidize it, right? We're going to oxidize the aldehyde, the primary aldehyde, and that's going to give us the carboxylic acid. And now from the carboxylic acid, we know thionyl chloride. So that's going to allow us to go to that leaving group that we wanted. And then we said, okay, now that we have this leaving group, we know a reaction that's going to allow us to exchange that CO with two carbons, right? So how we do that is we add two carbons and we make sure that that carbon that we add, one of them is nucleophilic, right? So there are two options we have, right? We either have this copper lithium option, or we have this magnesium bromide option. Okay? So which is the actual choice, right? Well, we know if we have magnesium bromide, this magnesium bromide is so nucleophilic that it would actually go and attack that carbonyl carbon, and we actually would get a primary alcohol. We would get an alcohol. Not a primary alcohol, but an alcohol. Okay, but we know that if we have copper lithium, that's not going to go all the way to that alcohol. We're going to stay at that carbonyl. So we can get rid of this MgBr, and we know it's going to be copper lithium. So if you've never seen this reaction before, what it actually is if you have any type of acid halide, which is a carbonyl, with a halogen, this X is a halogen, and you add two of these alkyl, you need two of these alkyl groups attached to one copper lithium, and all it does is it just replaces this halogen group with the R prime here. So only one of these R primes comes off the copper lithium. And what we get is that. So as you can see here, we're going from a chloride, which is the X, and we're replacing it with that R prime, which is what our intended product was, right? And the final step is to actually map out the synthetic pathway. We've already done that here. The only thing we need to formalize is replace oxidize with our oxidizing agent, which is chromic acid. That's your go-to if you want to oxidize something all the way. Go with chromic acid. So we started with the aldehyde. We wanted to make an leading group, so we had to go through the carboxylic acid. So we used an oxidizing agent, chromic acid. We add thionyl chloride to get our leaving group, and we added the copper lithium to go to our intended product. So again, I want to repeat the framework that we use to tackle any organic chemistry synthesis problem. The first step is what's the same and what's different. The second step is, now that we know what's different and what's the same, what are the specific changes that are made? The next question that we need to ask ourselves is, how do I make each specific change? And I want to keep in mind that making those changes may take multiple steps. You know, it's nice if it works out in one step, but they may take multiple steps, like what we did here. We're going from this hydrogen to the two carbons, but we had to go through the leaving group first, and then we had to go through the carboxylic acid first. So it may take multiple steps to make that change. And the last one is to formalize and map out your synthetic pathway, and that's what we were doing when we replaced our oxidizing agent with like our actual oxidizing agent, which was chromic acid. So if you can develop a framework and a systematized method for attacking organic chemistry synthesis problems, you know, it makes it a lot simpler. And you're not going straight towards the problem and not knowing what you're going to do. And it gives you a lot more confidence when you know exactly what your battle plan is. So hopefully that helped. And if you liked what you saw, please subscribe to this channel. Please like the video. And please comment and ask questions, because this channel, it's for you. It's not for me. It's to help you guys out. So if you can comment and ask questions, I'd be greatly appreciative, and I'd absolutely try my best to get back to you as quick as I can. So thanks for watching, and hopefully that helped. Till next time.